SpaceX is currently deploying thousands of satellites every few months, building out a global network at a pace that far exceeds any previous orbital project. This chart tracks every active, maneuverable satellite in Earth's orbit. One company, Starlink, now controls roughly 75% of them. With more than 10,000 operational units, the network generated over $11 billion in revenue last year from its 12 million subscribers. The service has been adopted for everything from commercial airline Wi-Fi to active war zones. As this image shows, soldiers are mounting these advanced terminals to muddy civilian vehicles to maintain a connection where traditional infrastructure has been destroyed. To justify the enormous cost of this deployment, SpaceX points to a total addressable market of $1.6 trillion. This valuation is built on the idea that Starlink can capture a massive share of the global telecommunications industry. However, that $1.6 trillion figure relies on growth projections that assume satellite internet can overcome massive technological and geographic hurdles. In reality, Starlink's expansion is already approaching two distinct barriers: the economic limits of the terrestrial market and the physical limits of our orbit. The primary issue with a $1.6 trillion valuation is the assumption that satellites can directly compete with fiber and cellular providers in dense cities. Because satellite bandwidth is shared among all users in a specific area, heavily populated urban centers quickly overwhelm the network's capacity. In a city where thousands of people are trying to connect at once, terrestrial networks will always be faster and more reliable. Analysis suggests a much smaller, lucrative $129 billion niche market of rural homes, maritime fleets, and remote industrial sites. There's also a $15 billion add-on opportunity, where Starlink works with terrestrial carriers to provide coverage in dead zones. Even in these remote regions, the service faces a geographic cap. The cost of launching a satellite remains the same regardless of the income level of the country it flies over. This makes the hardware inherently expensive for users in lower-income nations who lack government subsidies. Starlink works well as a specialized network for the edges of the world, but the underlying cost per subscriber places a hard limit on how many people it can actually serve. While the economics limit the customer base, the physics of the system limit the constellation itself. To keep latency low enough for modern internet use, satellites must operate in low Earth orbit, roughly 550 kilometers above the ground. This model shows the resulting congestion. There are now over 14,500 active satellites in Earth's orbit, a tenfold increase in just 10 years. Most of that growth has occurred in the specific narrow shells that Starlink occupies. This congestion is already causing problems for astronomers. As this photograph shows, bright horizontal lines from passing satellites now frequently cut across the star fields of the Milky Way, leaking radio noise and reflecting light that blinds ground-based telescopes. More dangerous is the risk of a collision. In low Earth orbit, objects move at 8 kilometers per second. If two satellites hit, they create thousands of fragments. If the density reaches a tipping point, we face Kessler syndrome, a chain reaction of debris that could make the entire orbital shell unusable for generations. Low Earth orbit is a finite resource, and it is rapidly reaching its carrying capacity. These two ceilings are linked. Starlink's economic model requires thousands of short-lived, mass-produced satellites to saturate the niche market, which directly contributes to the congestion crisis in orbit. This has created geopolitical tension. Because one company's footprint is so large, other nations are finding it difficult to secure safe orbital pathways to launch their own communications infrastructure. The response has been urgent. International organizations and the U.S. Department of Commerce are currently rushing to develop the Traffic Coordination System for Space, or TRASS, to prevent accidents in these crowded lanes. This congested environment is also uniquely vulnerable. Any deliberate disruption, such as an anti-satellite weapon test, creates debris that threatens every other system in that altitude band. It is the central paradox of the mega constellation. The network that provides critical disaster relief and maritime navigation is actively degrading the orbital pathways it needs to operate. Managing this shared orbital environment has become a requirement for keeping our entire world connected on the ground.